So here I will again look at the quality of Taylor approximations, and I will look at an application where I look at the quality of the Taylor approximations of the exponential function when n goes to infinity. So here again is Taylor's theorem. So what is, now I'm going through it a little bit faster. So we get a remainder term, which is a difference, the nth order remainder term, which is a difference of f with its nth order Taylor polynomial, where the Taylor polynomials are defined at some point a in the domain of the function. Now Taylor's theorem says that the nth order remainder can be expressed as such. So the nth order Taylor approximation can be defined as some n plus 1th order derivative for some psi x in ax, in between a and x. And we divide it by n plus 1 factorial times x minus a to the power n plus 1. Right? So that's just to recall and revisit Taylor's theorem, because we're going to use it and exploit it. So here is the other application. So now we take e to the power x, and we're going to look at Taylor approximations in a equals 0. So we know, and we already calculated those, right? So for the exponential function, it's a rather nice formula, right? So Tn of x is 1 plus x squared divided by 2 plus x to the power 3 divided by 3 factorial plus x to the power n divided by n factorial, right? So that's the nth order Taylor approximation for a equals 0. Right, so now the question is, how good are these approximations, right? So fx in terms of Tn of x. And what I would like to show is that these, in the end, these Taylor approximations are, for a fixed x, are going to be better and better. Okay, now we're going to look at and assume that x is larger than 0, where you could also take another value, but let's assume that that x is larger than 0. Then we know what is a larger element, x or a equals 0. So Taylor's theorem now says that there is an x, psi of x in between 0 and x, such that the remainder term can be expressed as follows. The remainder, what is the remainder? Well, it's the difference of fx and Tn of x. And this is the remainder term, right? So the remainder term is calculated as the difference between f and its nth order Taylor polynomial. Then this is equal to some f the nth plus 1th derivative at some point. And it is divided by n plus 1 factorial times x minus 0 to the power n plus 1, which then of course equals x to the power n plus 1, right? Okay, now we're going to use the fact that f is a very nice function. So we have fx is e to the power x, which means that all derivatives of this function take the same form and they are equal to e to the power x, right? So this means also that the n plus 1th derivative in psi of x is just equal to e to the power psi of x. So let's include that. So let's look at the difference, the absolute value of the difference between f and its nth order Taylor polynomial evaluated as some x. Then we get e to the power psi of x times x to the power n plus 1 divided by n plus 1 factorial, right? So we can leave out the absolute value signs here, since we know that x is positive, right? So that's due to our assumption that we are looking for values of x that are positive. Okay, but now we know that psi of x is in between 0 and x. So we know that since x is larger than 0, that e to the power psi of x is smaller than e to the power x. Here we just repeat the other term, x to the power n plus 1 divided by n plus 1 factorial. Okay, nice. This is we're almost there, because if you look a little bit closer to this term over here, you might notice, and I will show it on the next slide, that the limit of this term for n to infinity is 0 for any fixed x. So in conclusion, this means that the absolute value of the remainder term goes to 0 for any fixed x when n goes to infinity, right? So this means in particular that the Taylor approximations are getting better and better, right? So when n goes to infinity. Okay, so that's where this application ends. And now I will show that the limit for n to infinity of x to the power n divided by n factorial equals 0. Okay, the proof is something that we've already done in some way. It resembles the proofs using the ratio test a lot, but let's have a go. It goes pretty fast. So I will show that the limit of n to infinity for any fixed x of x to the power n divided by n factorial is 0, right? So I will just show you one way. Maybe you can come up with other proofs, but this proves is rather direct and works pretty well. So I define an as x to the power n divided by n factorial. So x is fixed. Yeah, so what we see then is that we take the absolute value of an plus 1 divided by an, that this equals x absolute divided by n plus 1, right? Okay, but x is a fixed number, so we can choose n so large that the fraction that we have here is smaller than 1, right? So we now choose n capital N such that we have x divided by capital N plus 1 is smaller than 1. Okay, that's the first step. And in that case, what we can see is that that the absolute value of the fraction a capital N plus 1 divided by an is smaller than 1, right? It's smaller than 1, but it's also smaller than this fixed term, which is the absolute value of x divided by capital N plus 1, right? It's smaller equal. Here it's exactly equal, right? Okay, so now we see that the absolute value of a capital N plus 1 is smaller equal than this fixed factor x divided by capital N plus 1 times the absolute value of a capital N. Okay, then in a similar way, we now are going to look at the fraction of a n capital N plus 2 divided by a capital N plus 1. And this one is really smaller than the absolute value of x divided by capital N plus 1. So we have now that this one is smaller than x divided by capital N plus 1. Right? So in turn of which we can say that the absolute value of a capital N plus 2 is smaller than this fixed factor x divided by capital N plus 1 times the absolute value of a capital N plus 1. Yeah, but we've already seen that this one is smaller. You see it on the line here. This one is smaller than this fixed factor times the absolute value of a capital N, right? So we have that this one is smaller equal than x divided by n plus 2. And we can make a smaller equal sign. We should have a smaller equal sign there. X absolute to the power 2 divided by n plus 1 to the power 2 times the absolute value of a capital N. And this way we can continue because we can also look at the ratio of the absolute value of a n plus 3 divided by a capital N plus 2, etc., etc. And then we will deduce that in general, we can continue and show that a capital N plus k is smaller than x absolute divided by n plus 1, capital N plus 1 to the power k times this fixed factor a capital N absolute, right? Okay, but now realize that this number here, this number, absolute value divided by capital N plus 1 is a number smaller than 1. So if we take powers of this number, we will see that this number goes down, right? So, and in the limit, so if we take a limit for k to infinity, then the limit is also 0, right? So we see that this number here goes to 0, and this one is a fixed one, right? So we've chosen a fixed capital N. So this number is going down to 0 times a fixed number, which then together goes to 0, right? Okay, so in conclusion, we have that if for high enough um, index numbers, we get that the limit for n to infinity of a capital N plus k is 0, right? Is 0. Yeah, but this means that in the long run, if we take n high enough, that an also is close to 0, right? So that the limit of for n to infinity of the absolute value of an is 0, right? And this means that the limit for n to infinity of an is 0. So this means that we've shown now that this result, that the limit for n to infinity of x to the power n divided by n factorial, that it's 0. Okay, that's it. That's the whole proof.